Hello everyone, welcome back to my channel. This will be the third video on gravitation, and in this video I'm going to talk about the gravitational potential energy. Now, the gravitational force between two masses, electrostatic force between two charges, or magnetic force between two magnetic poles shows its effect even when they are at a certain distance from each other. For this reason, the gravitational, electrostatic and magnetic interactions are also sometimes called action at a distance. Each of these three types of interactions can be explained in terms of the field concept. According to the field concept, a material body, when placed in space, sets up the gravitational field. So, the space surrounding a material body in which the gravitational force of attraction can be measured is called gravitational field. So, gravitational field. So gravitational field means the space surrounding a material body in which its gravitational force of attraction can be measured. Okay, that is known as the gravitational field. Now, intensity of gravitational field, or we say strength of the gravitational field. Now, let us consider Earth as a sphere. Let's consider Earth as a sphere of mass capital. Let us consider Earth. This is your Earth. Okay? We consider Earth as a sphere of mass capital N. Suppose we have to find out the intensity of the gravitational field due to the Earth at point P. So we want to find out the strength of the gravitational field due to the Earth, suppose say at point P, which is at the distance r, which is at the distance r from the center of the Earth. So which is at the distance r from the center of the Earth. Okay, so in order to do that, we will place a test mass. So test mass means like it's a body of unit mass. Okay, so we are going to place a test mass, say m, at the observation point P. So there is a test mass m at this observation point P. Now, according to Newton, the force of attraction between the two bodies, between the Earth and the test mass having mass small m, okay, is given by, according to Newton, the force of attraction will be G. Here G means the universal gravitational constant. So that product of the masses of the two bodies, so capital M into small m, by square of the distance between their center. So that is r squared. Therefore, the gravitational field, okay, due to the Earth at point P will be given by the gravitational field due to the Earth at point P will be given by E equals to, okay, so the gravitational field is defined as the force experienced per unit test mass. Okay, the force experienced per unit this test mass. That means test mass has a mass of small m. So the force is now given by G mm by r square. So here divided by m. So 1 by m. So this mm cancels out. So we have here gm by r square. Now, the direction of the gravitational field at the point P is directed towards the center of the Earth. So the E is directed towards the center of the Earth. Also, the intensity of gravitational field at any point is equal to the acceleration due to gravity at that point. So the intensity of gravitational field at any point, which is this one, okay? So it is equal to the acceleration due to gravity at that point. Now the next topic will be the expression. Let us find out the expression for the gravitational potential energy. Okay. Whenever two material bodies are present at finite distance apart, the system always possesses potential energy. It is because some work has to be done for bringing the two bodies from the positions where they do not exert any force on each other to their present positions. So the potential energy is negative if the two bodies are present against the force of repulsion, and it becomes negative if the force between them is attractive in nature. So in case of two material bodies, the potential energy is called gravitational potential energy. Now, so the gravitational potential energy at a point is defined as the amount of work done in bringing the body from infinity to that point against the gravitational force. Okay. Now, let us consider Earth. Let us consider Earth as a sphere. Okay, let me draw a little bit bigger. Let us consider Earth as a sphere of radius r and mass m. So we are considering Earth as a sphere, as a uniform sphere of radius r and mass m. Now, let's determine the gravitational potential energy of a body of mass small m, say, lying at a point A. So we're going to find out the gravitational potential energy of a body of mass small m lying at a point A. So mass will be given by small m. Okay, lying at the point A. Let us say that the distance of this point A from the center of the Earth is given by r. O is the center of the Earth. Let us say that the distance of this point A from the center of the Earth is given by small r. That means OA is equal to small r. Okay, so there is a body of mass m lying at a point A, which is at a distance small r from the center of the Earth. Now, from the definition, the gravitational potential energy of the body at point A will be given by work done in bringing the body from infinity to point A. So how much work is done in bringing the body from infinity to this point A? It gives you the gravitational potential energy of the body at point A. Now, so we are bringing the body from infinity. So infinity to the point A. Suppose at any instance, the body is at the point P. While bringing it from infinity, suppose at any instance, the body is at the point P. Suppose which is at the distance x which is at a distance x from the center of the Earth. So this point P is at a distance x, from the center of the Earth. Okay. This point P, let's say that it's at a distance x from the center of the Earth. Now, according to Newton, the gravitational force between the two bodies will be given by when the body is at P. Okay? So we are bringing the same body of mass small m from infinity. So at an instance, the body is at a point P. So here the mass of the body at P is also m. Then according to Newton, the gravitational force of attraction between the Earth and the body at point P will be given by F is equal to G, product of the masses, mass of the Earth into mass of the body by square of the distance. Here the distance between the point P and the center of the Earth is x. So we write here x squared. Now, then the small work done in bringing the body from this point P to another point Q through a small distance dx. So the small amount of work done in bringing the body from this point P to point Q through a distance dx will be given by small work done dw. So work done is given by force into displacement. Small work done, so small displacement. Now we have seen that F is now G capital M into small m by x squared into dx. Therefore, the total work done in bringing the body from infinity to point A. The total work done in bringing the body from infinity to point A can be obtained by integrating between the limits. Here, this point A is at the distance r from the center of the Earth. So we'll integrate this dw between the limits r to infinity. We are bringing the body from infinity to point A. So we have to integrate it between the limits r to infinity. Smaller here means distance of point A from the center of the Earth is smaller. So we are going to bring the body up to point A. So we have to integrate it between the limits small r to infinity. Therefore, the total work done in moving the body or in bringing the body from infinity to point A will be given by W equals to, we are going to integrate it from infinity, we are bringing the body from infinity up to the point A. Now point A is at a distance of r from the center of the Earth. So r of dw. So now this is equal to integration infinity to r to that g mm by x squared dx. Now here g is universal gravitational constant and mass of the Earth is constant, small mass of the body is constant. Okay, so we are going to integrate dx by x squared. So this is equal to, since g is constant, m is constant, small m is constant, so we'll integrate dx by x squared between the limits infinity to r. Now this is a definite integral because we are integrating it between some limits, okay, between the interval infinity to r, okay, between this interval. So I have recently uploaded a video on definite integrals, so I suggest you to watch that video, only then you'll be able to work this simplification. Now let me rub out the remaining part, the beginning part of this problem. Now, so this gives you GMM and here the limit of integration is infinity to r. Now dx by x square, we can rewrite it as x to the power minus 2 dx. Now we know that integration of x to the power n is x to the power n plus 1 by n plus 1. So this is equal to gmm, and integration of x to the power minus n is x to the power, x to the power n is x to the power n plus 1 by n plus 1 between the limits infinity to r. Now here what we are going to do is, instead of this x, we'll substitute the upper limit, minus, instead of x, we'll substitute the lower limit. So let me work out over here. So your work done W is equal to gmm. Here the denominator is minus 2 plus 1. Minus 2 plus 1 gives you minus 1. So minus 1 is constant. So I'm going to write here W is equal to minus of gmm. And x to the power minus 2 plus 1, x to the power minus 1, x to the power minus 1 means 1 by x between the limits infinity to r. Now we'll substitute the limits. So your work done is given by minus gmm. Here 1 by, first instead of x I put r, minus 1 by infinity. So that is minus gmm by 1 by r minus 1 divided by infinity. Infinity is something which is a very large quantity. So 1 divided by infinity will be 0. So 0. So I need not write 0. So this gives you W to be minus gmm by r. So this much work has to be done in bringing the body from infinity to point A. Now, this work done is stored inside the body in the form of potential energy, because potential energy means work done in bringing the body from infinity to the point A. I told you that, okay, as we started this derivation. So this work done is stored inside the body in the form of potential energy. Therefore, the potential energy U will be given by the work done, which is equal to minus G capital M into small m by R. Okay, so which is the required expression for the gravitational potential energy, okay, at any point which is raised to some distance above the surface of the Earth. Now, let's do a numerical problem basing on this expression. So, okay, let's write the numerical problem. Suppose the distance between the sun and moon, our sun and our moon, which is the only natural satellite. So the distance between the sun and okay, let's say instead of sun and moon, let's consider the earth and moon. Like, let's talk about the objects which are at closer distance. Okay, the earth and the moon, the distance is lesser as compared to the sun and the moon. So the distance between the earth and the moon is, let's say, 3.8 into 10 to the power 8 meters. Okay, let's say that the distance is 3.8 into 10 to the power 8 meters. So let's find out the gravitational potential of the Earth-Moon system. So, find the gravitational potential energy of Earth-Moon system. Okay, let us do this, okay, to find out the gravitational potential of Earth-Moon system. Okay, Now we have to know for the mass of the Earth. Okay, the mass of the Earth will be 6 into 10 to the power 24 kilograms. Okay, given mass of the Earth is 6 into 10 to the power 24 kilograms. So this is what we have to know. Okay, the mass of the Earth. Okay, the mass of the Moon is actually the mass of the Moon. Let me take a small m. Okay, it's something like 7.4 into 7.4 into 10 to the power 22 kilograms. I'm frequently moving away from the board so that you'll be able to see what I'm writing down here. Okay. And we have to know the universal gravitational constant, which is fixed. That's 6.67 into 10 to the power minus 11 Newton meters square per kilogram square. This is what we need to know. These are the values. Okay. Okay. Sometimes the mass of the Moon may be given, but mass of the Earth and the universal gravitational constant, okay, has to be learned. You have to know these values. Now we just have seen that the expression for the gravitational potential energy is given by minus Gmm by R, where here M and M are the masses of the two bodies, okay, and here R is the distance between the objects. Okay, we have just seen that expression, we derived it. So here the distance between the Earth and the Moon will be given by small r. Capital M mass of the Earth, small m mass of the Moon. So let us substitute the values and find out the solution. So here minus as it is, G means 6.67 into 10 to the power minus 11. Capital M, 6 into 10 to the power 24 kilograms. Small m, 7.4 into 10 to the power 22 kilograms. By distance r, r is 3.8 into 10 to the power 8. So we just let us solve the exponent part first. 10 to the power minus 11. Okay, let me write the remaining ones here. 6.67 into 6 into 7.4 divided by 3.8 into 10 to the power minus 11 plus 24 plus 22 minus 8. So minus 11 plus 24 plus 22 minus 8. Okay, of course there is a negative sign, okay, from the formula. Here negative sign means what? The gravitational force is attractive in nature. Okay, so if there is a force of attraction between the two bodies, then the potential energy becomes negative. So that negative sign indicates that. So after solving this, we can get the solution to be minus 7.78 approximately into 10 to the power 28 energy. So your answer will be in terms of joules. That's all. So in this video we have discussed about the gravitational potential energy and the expression for it, and basing on that we have done one application. So see you next time. Okay, so I'll be uploading more videos, so you please go through the videos, make some notes and learn something. Thank you.